Morning all. Hope you all are doing alright. Starting off, do we have any questions over the homework for section 4.3? $57 and $23. Okay. A and part of B. Okay. Yeah, I imagine the x-intercept portion of B on 57 is the difficult part. F of x equals, let's see, we have negative 4x squared minus 6x plus 2 and let's see, part A, we want to start off by finding the vertex. So h is equal to negative b over 2a. Now, b is already negative 6, so negative b makes it a positive 6. A is negative 4, so 2 times that would be negative 8. So taking 6 divided by negative 8, it gives us a negative 0.75. Now I left that as a decimal instead of a fraction because that'll be easier to plug in and calculate. Alright, so k, that means we want to plug in h to the function. So it'd be negative 4 times negative 0.75 squared minus 6 times negative 0.75 plus 2. If we square negative 0.75, that is 0.5625. Negative 6 times negative 0.75. What's that? 4.5. 4.5 plus 2. And negative 4 times that. We have 1, 2, and then 2.25, negative 2.25. So we end up with, what is that, 4.25 as k. So our vertex is negative 0.75, comma 4.25. For intercepts, for y, we plug in f of 0, which is 2. So 0, 2. That one's easy enough, so we'll go ahead and get that one. X, we know we set f of x equals 0. So negative 4x squared minus 6x plus 2 equals 0. One thing we could do here, just to make this a little bit easier, is divide everything by negative 2. So we do have that common factor. And I want to divide by negative so that we have a positive in front of x squared. So it would be 2x squared plus 3x minus 1. So 9, 8, wait. Yeah. Alright, so plug it into the quadratic formula. Negative 3 plus or minus the square root of 9 minus 4 times 2 times minus 1 over 4. So this is 9, and then this is minus 4 times 2 times minus 1 is plus 8, so negative 3 plus or minus square root of 17 over 4. And I would go ahead and approximate that number, square root of 17. It comes out to be 4.12. Maybe put the 3 on there. That's not a big deal. We won't be able to graph anything that precise anyway, but negative 3 plus 4.123, and then divide that by 4, so we get 0.28 as one of our zeros. And the other one, be negative 3 minus 4.123 divided by 4. Our second one is negative 1.78. And that's really the best we can do here, because the answers do not come out to be whole numbers. They don't even come out to be nice fractions. They're just infinite decimals, or irrational. But we can approximate the value at least and get some coordinates that we could plot. So we have the vertex, we have the y-intercept, and we have our two x-intercepts. Right, well, it's not factorable. That's part of the issue. And we just have to use a quadratic formula. Yeah. And we didn't really do a whole lot of that where our quadratic formula didn't come out to be nice whole numbers or close to it. Or, if we ever got to this, we would just stop. We wouldn't actually go forward and approximate it. But in this case, we do want to go forward and approximate the answer, is that we're still looking for coordinates that we can plot on the graph. Alright. So, let's see. -1, -2, and +1, +4. So our vertex is -0.75 and +4.25. Kind of eyeball this being right there. 0, 2, the y-intercept. X-intercept 0.28. So somewhere around there. And negative 1.78. Somewhere around there. So the graph will look something like that. Okay. Okay. Then we also asked for 23. Let's see, 23 of f of x is x minus 3 squared minus 2. Alright, so our vertex, we can see this is in standard form. So our vertex is the opposite of this number, so this will be a positive 3. And 25 also, okay. And negative 2. Because there's a positive number in front, that means it opens up. Now, we said opens up or opens down. The book said concave up or concave down, which basically means the same thing. Okay, concavity is the direction of the curve. That's something we study more in calculus. So if you just want to say opens up or opens down for right now, that's fine. And then we want to use that information to graph the function. 1, 2, 3, minus 2. So it looks something like that. Okay. That's all we had to do in that problem. Instructions may not have been clear. But essentially we can graph this the same way we were graphing problems in 3.5, which is we start off right 3 and down 2, and then draw our parabolic curve going up from there. That's what the vertex represents and the fact that it opens up. So in 25, f of x is negative 2 times x minus 3 squared plus 5. In this case, our vertex, positive 3, positive 5. So again, we take the opposite of what's in the parentheses, and then we keep the same sign as what's after, and that's our vertex right there. Because this is a negative in front, excuse me, we know that the graph opens down. So 3 right, 5 up. And then we draw our graph going down from there. And we know it also has been stretched, so I tried to draw it a little bit more narrow. I didn't do a great job of that, but you can kind of see it there. All right. Other questions on homework? Today we're going to finish the rest of section 4.3, and then we'll also look at section 4.4. The first concept that we have to look at in section 4.3 is that of a maximum and minimum values. This is sort of related to our discussion from chapter 3, where we had local and absolute maximums and local and absolute minimums. In the case of a parabola, if we just look at the two problems we just graphed, we can tell this is going to be the minimum. This is both a local and an absolute minimum here. We don't really give it a local or absolute designation. We just call it the minimum in this case of a parabola. And we can see in this case that this coordinate is the maximum. Now, one thing we notice is that in both cases, that's the vertex. The vertex is always either the minimum or the maximum of the parabola, or of the quadratic equation. In this case, the vertex is the minimum because the graph opens up. That makes the vertex the lowest point in the graph, and in this case, because it keeps going up on both directions, it goes to infinity, so in that case we say there's no real maximum. Okay, so we have a minimum but no maximum. And it's backwards, or it's the other way around here, because now we have a parabola that opens down, therefore we have a maximum at the vertex but then no minimum. So in this case, we can summarize it as it always occurs at the vertex, so regardless of which one it is, we have to find the vertex. And then 1, if it opens up, then we have a minimum at the vertex. And 2, if it opens down, then we have a maximum at the vertex. Which really summarizes what we saw in those graphs. Now, whenever we say maximum and minimum, specifically we're interested in the y value, because that is now either the highest y value or the lowest y value on the graph, depending on which way it's going. Although we may also include the full coordinate, especially if we're not quite sure which part we're interested in. So we could say, in problem 25 here, the maximum is 5, which is true. Or we can say we have a maximum value of 5 that occurs at the point 3 comma 5, or 3 comma 5 is the maximum, we could say. So there's different ways to express it. Normally we would either ask for the coordinate or for the y value specifically. And at least for this question on the test, I usually ask as a multiple choice question. Yeah. So we're on page 310. And let's go ahead and look at problem 66. We're given f of x is negative 2x squared plus 12x. Now, first thing that we want to decide is which direction does the graph open? Opens down. Good. And because it opens down, is it going to have a maximum or a minimum? Maximum, yeah. Okay. Yeah, because if we know it opens down, our parabola has to look something like this, and so that's going to be the maximum value right there at the vertex. Okay. So let's calculate what the vertex is. So we said h is negative b over 2a. B is 12, so negative 12 over 2 times negative 2. And that gives us a value of 3. So we start off with a value of h equals 3. Sorry, I got something in my eye here. Probably sleep. Anyway, k is now equal to f of 3. And so we'll take our 3 and we plug it back into the function. So we'll have negative 2 times 3 squared plus 12 times 3. Make sure we square the 3 first, and then we multiply by whatever else is in front. So that's negative 2 times 9, this will be 36. So negative 18 plus 36, that will give us a value of positive 18. And so we can say we have a maximum at 3 comma 18. And specifically, we have a maximum of 18. So 18 is the highest possible value this function can give us. Every other value of x we plug in will give us a lower value than that. Now the maximum and minimum ends up being a very important point in applications. In fact, anytime we have what we call optimization problems, these always occur at local maximums or local minimums, which in this case, this is a local maximum, as it turns out. So if this function was representing profit, for instance, this is where profit would be maximized. Okay. More likely, this would be like a revenue function, though, but same idea. All right. Now, looking at number 68, similar question. We have f of x is 4x squared minus 8x plus 3. Which direction does the graph open? And then do we have a maximum or a minimum in this case? Right, this one will open up and therefore have a minimum at the vertex. And also have no maximum. As we can see with the parabola that opens upward, we're certainly going to have a minimum at the bottom of the graph and no maximum as the graph keeps going up and up to infinity. Alright, so once we establish that it opens up and has a minimum, then we'll just find the vertex like before. Negative b, well, b is negative 8 already, so negative b will turn that into a positive 8. 2 times 4 on the bottom is also 8, so h is 1. And then for k, we'll take that 1, plug it back into the function. So 4 times 1 squared minus 8 times 1 plus 3. 1 squared is just 1, and then multiplied by 4 gives us 4. Minus 8 plus 3. Let's see, that's negative 4 plus 3 is negative 1. So our vertex is 1 comma negative 1, so we have a minimum. Minimum at negative 1 comma 1, or we could say we have a minimum of negative 1. Okay. You know what? I switched that by mistake. That's my bad. I heard the second part correctly. Did not write the first part correctly. Yeah, 1 comma negative 1. Okay. Now, After that, what we look at in the rest of 4.3 and 4.4 are applications of these quadratic functions, and more importantly, applications where we want to find either a maximum or a minimum value. I would like to look at problem 92 on page 311. So we're in the same section still. The daily revenue R achieved by selling X boxes of candy is R of X equals 9.5x minus 0.04x squared. The daily cost C of selling X boxes of candy is C of X equals positive 1.25x plus 250. So they've given us a revenue formula and a cost formula. Okay. A, how many boxes of candy must the firm sell to maximize revenue, and what is the maximum revenue? Okay. So part A, we would like to maximize revenue. Now, because they're telling us to find a maximum, that means that this should be a downward opening parabolic curve or quadratic function. Notice for R of X, X squared has a negative coefficient. Also notice they switched the order on us. I don't know if they're trying to trick us or that's just how they wrote it. But we do recognize that this is actually our A value and this is our B value. Because A is always in front of X squared and B is in front of X. So we have to notice that's backwards, so that's why it opens down and therefore has a maximum, because A is negative. But in this problem, since the parabola opens down, they're only going to ask us to find the maximum because that's the only one that exists. We're not going to be asked to find a minimum, and realistically, we would never be interested in a minimum revenue calculation. Generally, revenue is not going to be lower than zero anyway, because if we don't sell any items, then we've essentially brought in $0 for our company. So we don't really need to calculate anything to know that, but we do need to figure out where it's maximized and how we can have a maximum amount of money being brought in. Now, because we're finding the maximum, what are we going to have to find in order to figure that out? Where is this actually going to happen that we have a maximum value? What do we call that point where it happens? vertex. Good. So we have to figure out what the vertex is. So h will be negative b over 2a. And again, keep in mind b is first and a is second because they've changed the order of how we normally see these. And if we want to, feel free to rewrite this to where it's in the standard order. So negative b would be negative 9.5, and 2 times a would be negative 0.08. Okay. Dividing those, we get 118.75. Now, whenever we're working an application problem such as this one, there is something else that we have to consider. Remember that the value here is basically our x value. Okay. And x in this case represents the number of boxes of candy that we've sold. So is it reasonable to think that we could sell 0.75 of a box of candy? Well, not really. We don't really sell candy by 3/4 of a box, and if we did, there'd be no way to sell the remaining quarter of a box because no one wants to buy an open food package. So instead of saying 118.75, what do you think would be a better number we could use to represent the number of sales that will give us a maximum revenue? 119, yeah. We have our choice really of 118 or 119, but realistically we see that our number is closer to 119, so we'll round it accordingly. Now, if we had gotten 118.5, then both 118 and 119 would have given us the same maximum value. But luckily it is closer to one than the other, so we can choose accordingly. So we'll take that 119 and plug it back into our revenue formula. So when we're working in applications like this, we actually do want to round that to a whole number. Okay. So we end up with a maximum revenue of $564.06. And I went ahead and just did all the calculations in the calculator. Again, don't have to write down every single step as long as I can see what you're doing. So something like that is fine, where we square the number and then multiply by negative 0.04, write that down, and then multiply those, and then add them together. Okay, so if this firm can sell 119 boxes of candy, they'll achieve a maximum revenue of $564.06. Now, Part B. Part B wants us to find the profit function, P of X. Because it turns out that what's the company generally is going to be more interested in is maximizing profit, not revenue necessarily. And we'll talk about why once we find Part C and solve that. So P of X, the way that we calculate that is taking our revenue R of X and subtracting our costs C of X. Okay, so we're saying if we take the money that we bring in and subtract the money that we pay out, then what's left is our profit, whether it's positive or negative. Anyway, so we plug in R of X, which is negative 0.04 x squared plus 9.5x minus C of X, which is 1.25 x plus 250. And so subtracting those, let's see, we have 9.5x minus 1.25x, so that would be 8.25x. Oh, I'm kind of off the screen there, sorry. 8.25x, and then minus the 250. Okay, so that's our profit function P of X. Let's look at this revenue and cost function a little bit more closely. When we look at our revenue function, revenue is generally considered as X times the price. Now, in this case, X is the number of items sold, and then the price here is calculated as 9.5 minus 0.04x. Now, what that means, sometimes we call this the demand function in parentheses. That means that the more items that we sell, the lower the price we can offer the item at. Okay. So, with 119 boxes of candy, we would take 9.5 minus 119 times 0.04. So, we're actually selling these boxes of candy for about $4.74. Okay, plus tax, I assume. So that's one thing that we can discern from this revenue function. Now our cost function tells us that when we see 1.25 times x, that's the price it takes to produce one box of candy. So we're paying $1.25 to produce each box of candy, and then the 250 represents what we call our fixed costs, and these are things like any rents that we have to pay, or whether we own or rent the place where we're selling this candy. It's either rent to the owner of the location or taxes to the government if we do own the location. It's kind of not the same thing in most cases. This variable cost is based on how much it takes to produce a box of candy, and that also includes paying our employees to help manufacture or put them together or whatever it takes there. Also includes the materials to create the box itself, and then also the candy inside. Okay. So each box costs $1.25 to manufacture or produce or whatever we want to call it. Plus, to cover the additional costs, that's why we need a higher price, $4.75, to pay for that. We're not just paying for the cost of a single box of candy. We also have to make sure we're paying our rent on time. Okay, and also the any capital we have is included in this. So if we're using machines to help produce the candy, the upkeep of the machines is it's really two different things. If we have to replace machines, that's over here. Upkeep of machines is over here. It's an interesting thing, an interesting process. Anyway. But putting it all together, we are able to create a profit function. And so in part C, they want us to maximize profit. Okay. Now, let me rewrite profit since I'm on a new sheet of paper. Negative 0.04x squared plus 8.25x minus 250. Yep. And so we want to find the maximum, and again, that means we need to find the vertex. Yeah, it's nice to have applications. I mean, they're not the easiest problems generally, and I know students don't like them from that point of view always, but I think it always is nice to provide some context as far as how we're actually using some of the math that we're learning. A lot of the stuff that we do, unfortunately, the real applications we don't see until we get to like a calculus or physics or engineering class or chemistry or whatever. Unfortunately, we just don't see all of the applications until we can have a better understanding of this material. But we like to introduce some relatively simple ones here that can maybe enhance our understanding of the topic, which is good. All right. So we start off negative b over 2a. That's our vertex formula. B is 8.25, so negative 8.25. A is negative 0.04, so double that, so negative 0.08. So it's like 8.25 divided by 0.08, and that's going to give us a value of 103.125. So, realistically, again, we wouldn't be able to sell 103 1/8 of a box of candy, so we should just round this to 103. So we will be able to maximize profit at 103 boxes of candy. Now, one question we might have then is, we looked at revenue, and it took 119 boxes to maximize revenue, but we see here it's only 103 boxes to maximize profit. Well, what happens is that, you know, our profit takes into account revenue and cost. And so what is happening in this case between 103 and 119 boxes specifically is what we call diminishing returns. And the idea is that we are able to increase our revenue going from 103 to 119 boxes, but the problem is we're actually increasing our cost even more in that interval. Revenue is still increasing, but cost is increasing at a faster rate between 103 and 119. So overall, we are increasing revenue, but we're actually decreasing profit in that interval. So we call that diminishing returns. Our returns that we get are decreasing, even though we are increasing our revenue in that window. And so it actually means we don't have to sell quite as many to maximize the money that we bring in as profit. So while it's nice to have a higher revenue, that's not always the best goal to shoot for. We want to have the highest profit. Definitely August. Yeah, supply and demand is. This is now an economics lecture. Supply and demand have a kind of interesting interplay where, if we have high demand, there's different reasons that can occur. One, the item is not being sold at a high enough price that we could actually increase our profit while selling less items, which is strange, but true. It also means that maybe we artificially created that demand by shorting the supply on purpose. We frequently see this anytime you have a game console release. We have high demand but low supply. In that's case, it's not really done on purpose. It's really a question of logistics at that point, because it's a matter of how many they can easily produce at a high quality to be able to sell, and not at the same time not overload the market for it and completely overestimate the demand. Now, in some cases, we can increase the number sold and increase profit. It depends on the curves that we end up working with for the demand curve and the supply curve. Yeah, it's ideally we would like our demand and our supply to be the same thing. That way we don't have a lot of extra product sitting in warehouses. But it's better to have more demand and lower supply than to have lower demand and higher supply. So sometimes companies will aim a little bit lower than hitting that break-even point. That way they can ensure they sell all the items that they have produced, so they don't have any extra hanging around, and have a relatively high profit. Even if they're not quite at the maximum, if we don't sell all of our items, we're taking up warehouse space, and then that's an additional cost that comes back to us later. And then one of the crazy things that we'll see that stores do. And this is frequently with like clothing stores will do this. Is they'll actually sell items at or below cost because it's more profitable for them to get that item out of the store and put newer items that have higher demand on display in their place. Especially when you go from one season to the next. So we're kind of transitioning to fall. Maybe. We'll see. We'll see what the day holds for us. Maybe it will be fall weather. Maybe it'll be summer weather. But all over a clothing store have fall clothes out, and maybe some winter clothes as well, because we're not that far away from winter either, given such a narrow fall window that we have in Midland. And so, if they have anything left from summer, they're going to sell it at a very low price, even at or below the cost that they paid, because it's more valuable for them to get rid of that product that they have and put the newer products out that have higher demand and are actually marked up quite a bit. Yeah, that's crazy, Rob. It's hard to think about right now. Snow coming, come on. But it might. So yeah, I mean, there's all kinds of factors at play when you run a business, especially a larger business, a larger scale business. I couldn't imagine. I couldn't imagine running a small business and not going crazy, but I sometimes get bogged down in details I don't need to. That's why it would probably be a maddening thing for me to do. Another example of diminishing returns, since we were talking about that before, it's like when you're studying for a test that you have at 8 a.m. the next day, and it's already 2 a.m. This is your diminishing returns point of studying, because at that point it's probably better just to get some sleep than to study a little bit more. So there's another example of diminishing returns for you. Okay. So getting back to our profit problem here. We know that it takes 103 boxes of candy for us to maximize profit. So we'll just plug that into the function. Negative 0.04 times 103 squared plus 8.25 times 103 and then minus 250. Alright, so 103 squared multiplied by negative 0.04. Put that up here. Then add 8.5 times 103 and then subtract 250. So that will give us a profit of $201.14. Absolutely, August. And I'm that same way. So, some people might have more energy for cleaning than others, but I know that's not me. Honestly, it's better if you keep it up a little bit at a time than try to do it all at once. I think. I don't know. It depends on the person, too. All right. So that wraps up that question. Yeah. Alright. I have two problems I want to do from chapter or section 4.4. I don't know that I have time to do them. I'm going to pick the easier, well, not easier. I'll pick the shorter of the two, and we'll do that one today, and then I'll save the other one for Monday next week. So, I don't know, y'all might be okay with this other one. Well, no, maybe not. Nah, yeah, we'll hold off on that one. Alright, so, I know we finished that at least. I'm going to, on page 318, look at number 10. We want to, we have a farmer that has 2,000 meters of fencing, and he or she wants to enclose a rectangular plot that borders on a straight highway. If the farmer does not fence the side along the highway, what is the largest area that can be enclosed? So we have 2,000 meters of fencing. And where our land, of course, is alongside a highway, so we only need to construct three sides. Okay. So, what I'm going to do is I'm going to label this side X and this side Y. Now, if this is a rectangular plot of land, that means this side is also X, because the opposite sides have the same length in a rectangle. Okay. So, first of all, what is our area of a rectangle? Length times width. And in this case, we've identified the length and the width as x times y, so we can say area is equal to x times y. Now let's look at our fencing. We know we have 2,000 meters of fencing, And we're going to use that 2,000 meters to construct these three sides. We don't have to construct the fourth side because the crops aren't going to run out into the highway. We still might fence that realistically, but we're considering that we don't in this case. So what formula can we use to describe the three sides that we have to construct here with the fencing? Two x plus y, yeah. Now, in order to enclose the biggest area possible, we're going to use all 2,000 meters of the fencing to build these three sides. This is kind of like a perimeter, except we know that we're not fencing that fourth side. So instead of perimeter, we just think about it as the amount that we're actually fencing. So it's two of these sides that are length x, and one side that is length y. So 2x plus y equals that 2,000 feet or 2,000 meters of fencing that we have. Now, we have two equations now, but the problem is both of our equations have x and y in them. And ideally, when we calculate area, we wanted to have one variable, either just the x's or just the y's. We don't really care which one, as long as we have just one variable. Now, that means we can take this equation that we have for our fencing now, 2,000 equals 2x plus y, and we can solve it for either x or y first. And then once we know what x or y is equal to, then we can substitute into the area formula so that our area just has one variable, not two. Which of these looks easier to solve for, x or y? Yeah, y would generally be easier because it doesn't have a coefficient. If we solve for x, we'd end up with a fraction. So we definitely would prefer not to have a fraction in our problem. So let's solve for y instead. Okay, and we'll do that by subtracting 2x from both sides. So we can say y is equal to 2,000 minus 2x. Well, now that we know y is equal to 2,000 minus 2x, we can replace it in our area formula. So our area is x times 2,000 minus 2x. And so that becomes a quadratic equation. A equals 2000x minus 2x squared. Okay. Well, now that we have a single variable, we have single variable x instead of having two different variables x and y. With a single variable, now we can find a maximum like we were doing in the last section. But this is now a quadratic formula, which we know is going to be maximized at its vertex. And this will be a formula where it opens down. Okay. Specifically, it'll look something like this. It actually goes through the origin and at some other point over here, 1,000 I believe. And then in between, we should have our highest point. Okay. So again, we had said y was equal to 2000 minus 2x, and we said area is equal to 2000 x minus 2x squared. And we want to maximize area. Now, our maximum occurs at the vertex. Actually, this is x. If we want to be more specific, we're actually finding a value for x here. Negative b, again, this is out of order. This is b, that's our a. So that'd be negative 2000. A is negative 2, so 2 times negative 2, absolutely, is negative 4. So side x will be 500 meters. Now that we know x is 500 meters, we don't really have to plug that into our area formula again to find the k value for the vertex. If we just want to find y, we can plug in the x that we just found, 500. And so we get 2000 minus 1000. And so y is equal to 1000 meters. And our overall area is 500 times 1000, which will be 500,000 square meters. Okay. In this case, I think it's easier, since we have this formula for y already, to actually just take our x that we get and plug it in there and get our y. That way we have the dimensions of the field, and we can multiply those to get the area still. Now, in these questions, it really depends what's being asked for. Sometimes they just ask for the dimensions. Other times they'll ask for the area. Sometimes they'll ask for both. So it's nice to be able to find all three. That way we know we can respond accordingly. Okay, August, you said you wanted the previous side. Did you all have any questions on this one? Any questions? Or not August, that was Amanda, I'm sorry. Okay, good. Okay, so go ahead and look at these problems. This is very similar to what we did today. Two problems on just finding maximum and minimum, the problem on the business, and the problem on the farmer with the field. So we'll look at those. I have one more problem I want to do on Monday for section 4.4, and I'll wrap up 4.4, and then we'll move forward to 5.1. Okay? Well, you all have a good rest of your day, good weekend, since today's Wednesday, and I'll talk to you on Monday.